Alright, this video is going to focus on hybridization. We talked about this a little bit in class on Tuesday. It's based on what's called valence bond theory, and there's some debate out there as to whether this is truly the best explanation for what's happening when a bond is formed, but it's one that makes sense with the geometries we've talked about, so we're going to go ahead and discuss it for the purpose of this class. The thought is that when electrons form a bond, the orbitals in which they're in have to overlap in order for them to be close enough to make a stable connection. They do want to minimize their relative closeness, but if they don't overlap at all, they can't really form a bond. And I'm not sure why this isn't clicking, but we'll try it again. Alright, there we go. So what you see here is that if they get super close to one another, you're going to have to provide a source of energy for them to want to stay in that close contact. So there's a lot of repulsion if they're super close. And if they don't overlap at all, then you're really not going to have any energy change because they're really not going to make a connection. So you do want there to be some overlap, and we see that as that overlap becomes closer and closer, eventually you reach kind of an optimal overlapping that results in a release of energy. It's typically when you have a shorter bond length, and that's going to be the point at which your electrons are most willing to be in contact with one another, and that bond is going to be formed. So what we see when we have four pairs of electrons that need to share three-dimensional space, we need to have four different orbitals in which those electrons can be placed. And so we always start with our lowest energy orbitals first, which would be S, and then we work our way up to P. And depending on where those valence electrons are, they could be in 3s, 4s, 5s, 6s, it doesn't matter. It would be that S along with the P orbitals associated with it that would overlap, and that causes the dumbbell shape of the P orbitals to become a little more spherical, and that's where we see that tetrahedral geometry coming from that we see with the four areas of electrons around the central atom. Now, if you happen to have a double or a triple bond, we're going to talk about that in a little bit as well. We will see that one of those bonds in the double bond and two of them in the triple bond actually form above and below the nucleus, or between the internuclear space between the two atoms, and so they would not be applicable. They would still fit into that one hybrid orbital. So if we have only three areas of electrons around the central atom, such as with boron, or maybe if we had a double bond between, say, sulfur and oxygen in SO3, we only need three orbitals to create that hybridization, and when we have the S and the two P orbitals do that, we make that trigonal planar shape. We see the P dumbbells have gotten a little larger and more spherical-like, and so we have the sp2 hybridization for any atom whose central atom has three areas of electrons surrounding it. When you have two areas of electrons surrounding your central atom, then you need two orbitals in which that can kind of overlap to cause that bond to form. And so if we take an S and a P orbital, sp hybridization, we can have that bond form. We talked about in period 3 or higher, where you can have more than four pairs of electrons around the central atom. You can have 5, possibly 6. And when that occurs, you're going to need to borrow from your d orbitals. We talked about that a little bit already. And so you can see that there with the trigonal bipyramidal shape for the sp3d hybridization. And then if you happen to have a 6th pair, you would take 2 d orbitals, and that's how sulfur is able to do the octahedral shape. There it says D2sp3. You can also call them sp3d2. I think I changed that this year, so they would just go in order. But yeah, it's just that is not something to get too stressed out about. Whether you put the D's in the front or behind makes no difference. So I forgot to put this in your notes, but what we're going to do is go back and look at some of those structures we talked about in the last section, and we're going to label the hybridization of these molecules. So again, double and triple bonds count the same as a single bond. We're just looking for areas of electrons around that central atom And what we see with phosphorus is it has 4 areas of electrons around the central atom. So it would need 4 different orbitals for those electrons to be placed in, and that would be sp3 in terms of its hybridization. In NF3, we have 3 areas that are shared, and we have 1 lone electron pair, so a total of 4 areas of electrons around the nitrogen atom. So it would have also an sp3 hybridization. In ClO3-, we have 3 areas of electrons that are shared around chlorine, and then the 1 lone electron pair. So it too would have an sp3 hybridization. And ClF3, this time we're a little bit different because this is one of those that does not follow the octet rule. We have 3 areas that are shared, 2 that are lone pairs, so that's 5 areas total. And so we would need a d orbital along with the s and the 3 p's to fit all these electrons into. So this would be sp3d hybridized. In BCl3, only 3 areas of electrons surround boron. So we only need 2 p orbitals along with the s, so we get sp2 hybridization. And then in SF6, we have 6 different areas of electrons around sulfur, and so we would need 2 d orbitals along with the s and the 3p. And the last thing we're going to talk about, one more. In Cl3-, there's 5 areas of electrons around the chlorine, 3 lone pairs, 2 shared pairs, and so that would give us an sp3d hybridization for this molecule. The last thing we're going to talk about on this video is what happens when we are sharing multiple pairs of electrons. Another way these bonds can be described as sigma or pi bonds. Sigma bonds are bonds that are found directly in between the atoms, and that's along the axis. That's when we tend to have the hybridization taking place. But there is some space above and below when we have the hybridization occur, and you can see there in ethylene how there is a location above and below where another bond can form. In this particular molecule, you just have a double bond, and so that's why you would have 1 sigma between the 2 carbons, and you would have 1 pi bond between the 2 carbons, representing the single bond that's initially present and then the double bond that follows. The carbon-hydrogen bonds would also be considered sigma bonds because there are 4 single bonds connecting the carbons to the hydrogen atoms. So this molecule as a whole would have 5 sigma bonds and 1 pi bond. If you happen to have a triple bond, you would have 2 pi bonds. So here's a new molecule, CO. Carbon has 4 electrons, valence electrons, oxygen has 6 for a total of 10. And the only way you're going to get 10 electrons for both of those atoms to get 4 pairs is to make a triple bond. And so because you only have that 1 bond in carbon monoxide, you would have 1 sigma bond and 2 pi bonds present. 2 pi bonds present. Sorry, making back-to-back videos is starting to lose the tongue. C2H4, this is the ones you did in your lab. And you saw when you drew this one that if you did not make a double bond between the 2 carbons, you would not get enough electrons assigned to those carbon atoms. So in terms of sigma and pi bonds, every single bond again is a sigma bond. So we have 4 single bonds between the carbons and hydrogens, and we have a double bond between the 2 carbons, so that counts as a 5th sigma bond. And then the pi bond would come from the double bond between the 2 carbons. Right, and I believe that's the end of this video, and we'll talk next about formal charge and resonance.